Okay, now that we've kind of got basic differentiation, basic integration down, we had a version of Taylor's theorem that allowed us to approximate a n times differentiable function with a n degree polynomial. We're going to work on moving towards the series, Taylor series now. So if I have an infinitely differentiable function, I can get a power series that is actually equal to that function on an interval of convergence. So to do that, well, I have to be able to add up sort of infinitely big polynomials, and we have to take a limit of polynomials in some sense then. So we need to talk about convergence of functions, and there's sort of two ways we could do this, and one is sort of a good way and one is sort of a not so good way. Let's deal with the not so good way first and kind of see why it's a not so good way. So let's look at pointwise convergence first. So if I'm going to have convergence, there has to be a limit of some sort, and this is convergence of functions. So I've got a function, a sequence of functions. So we're going to let f sub n mapping some set E, and let's take real valued functions be a sequence. I have one of those for each n value, sequence of functions. We say f sub n converges to f pointwise if given epsilon greater than 0 and x in the domain, we can find n in the natural numbers such that for n bigger than n, the absolute value of f sub n at x minus f at x is less than epsilon. Okay, so let's look at this a little bit. So this n value that we find, it depends on both epsilon and x. Okay, so this is kind of like convergence at a point, right? At convergence at a point, I got to pick the point, and I got to pick epsilon, and then I had to find a delta that worked for that point and that epsilon. It's sort of the same thing here. I pick a point and I pick an epsilon. I have to find an n that works for both that point and that epsilon. Uniform continuity was a little bit different. Uniform continuity says all I had to do was pick epsilon. I could find a delta that worked everywhere. So pointwise convergence is sort of like continuity at a point. The other convergence we'll talk about is called uniform convergence, and it's sort of like uniform continuity. I pick an epsilon and I get an n value that works everywhere for that epsilon. Okay, so let's see an example of this and sort of why it's useful, but it's not so useful as uniform convergence. So here is going to be my sequence of functions. Let's put some x values in here. So say 1, 2, 3, 4, 5, 6, 7, and we'll say this is at 1. My first function, it's going to be 0 up until 0. At 0, I'm going to go linear up until I get to 1 at 1, and then back down to 0 at 2, and then flat from the rest of the way out. Okay, so this is going to be f1 of x. Then my next one, it's going to be 0 here. Oops. It's going to be 0 here until I get to 1, and it's going to do the same thing. It's going to go up to 1 at 2, and then back down to 0 at 3, and flat for the rest of the way out. Okay, the next one, similar. Kind of got this triangular wave that's sliding to the right as my functions increase in subgroups. So this is f sub 4 of n. This is f sub 3 of, oops, not n, of x of x. This is f sub 2 at x. Your next one, it's going to slide here, go up, come back down, keep going. It's f5 of x, and so on, right? So eventually I get out here and I've got this thing that goes this way, and this is going to be at n, the peak of the triangle is f sub n at x. Okay. Let's see if we can prove that this converges pointwise to 0. So this set or sequence f sub n of x converges to 0 pointwise. Okay, so let x in R, then for n bigger than, say, x plus 2, just f of x, f sub n of x is equal to 0, right? N is where the peak of the triangle is, so if I put the triangle 2 past x, x is always going to be at least one step behind where the triangle starts increasing. So it will always be 0, which goes to 0 as n goes to infinity, right? Okay, so that means that this function converges to 0, but in some sense every single one of these functions is the same distance away from the 0 function, right? They all have that triangle area that they're different than 0 from. So in one sense all of the functions are far away from 0, but pointwise they do actually go to 0. That can cause some problems when we have something that's not quite as nicely propagating off towards infinity, and we kind of push all of the pathologies away. We can see other sequences that kind of do this same sort of thing. Let me draw another sequence that sort of does the same thing, but then it causes problems at 0. So let's have the same sort of idea. Here's 1, here's 1/2, here's 1/3, 1/4, and so on. I'm going to have 1 over n stuff. It's going to get closer and closer to 0. And what I'm going to do is our first function is going to be 0, and then it's going to come up and go like this. And the heights of all of these are going to be the same. We're going to have a height of 1 for each of these things. The next one, instead of between 1/2 and 1 it going up, what it's going to do is it's going to go up between 1/3 and 1/2. Okay. And the next one, what it's going to do, it's going to go up between 1/4 and 1/3. And the next one's going to go up between 1/5 and 1/4, and so on. So down here I've got like really spiky thing in there, and eventually we see that this thing goes to 0. But when I sort of look at 0, the value that I'd want f of 0 to be, f of 0 is always 0. But no matter how close I get to 0, there's always going to be functions that have values up here near 1. And that's going to kind of blow up continuity at 0. So things kind of break, right? But we sort of break continuity at 0. And I could maybe even break it worse if instead of having like this red area just being a maximum of 1, maybe I wanted this to be an area of 1, so it had to go up to 3 or something. And maybe I make this bigger so that the area under the orange curve is bigger, and the area under this one is bigger, and the area under this one's bigger yet. And then I really blow stuff up as I get close to 0. I don't really know what would happen at all there. So we can have these sort of pathological pointwise convergence things where pointwise it converges to the 0 function, but sort of otherwise this sequence of functions gets really kind of weird as the sequence gets bigger. Okay, the book has some really good examples of these. I'm not going to go through all of them, but I'm going to have you read them. Okay, so let's see what would be a better version of convergence for us to work with. And it might not be the best version, but it's probably better most times than pointwise convergence. It's harder to achieve because it tells us, it gives us more restrictions. I don't get convergence when I have pictures that look like this. But when I do have convergence in the uniform method, I can say a lot about continuity, and I can say a lot about differentiability and integrability, which is going to be important for us when we're working with the Taylor series or the Taylor theorem that expands to the series. So uniform convergence. So we say that f sub n, we'll take a function from E into R again, converges uniformly on E if given epsilon greater than 0, there is an n in the natural numbers such that I should probably say to what it converges to f, such that the absolute value of f sub n at x minus f at x is less than epsilon for all x in E. Okay, so the for all x in E, this is sort of an if and only if and only if the supremum over x in E of the absolute value of f of n of x minus f of x is less than epsilon. So sometimes we'll see it just, we'll look at the individual points, and each point has a distance from f to f sub n less than epsilon, and all of them together, if I look at their supremum, the biggest one, it's also less than epsilon. So these are kind of equivalent, and they're both useful in how we prove things with uniform convergence. So let's look at an example now picture-wise. So say the function that I want to converge to is this function f. Okay, I need all of the points, and let's say we just want convergence from A here to B here. So say E equals this interval from A to B. Okay, what we're going to do is we're going to take epsilon bigger than 0, and I'm going to kind of get an epsilon envelope around this function here. I'm going to go up epsilon and down epsilon, up epsilon and down epsilon. and I'm going to do that from A to B. So I've got this kind of f plus epsilon part, and I've got this f minus epsilon part, and a sequence converges uniformly if eventually, so I don't care really what happens outside here, but as long as I'm in here, I'm between the red stuff near f. And then once I get out there, I can do whatever I want. So maybe this is f sub n. Maybe the next one, what happens is we come in from down here and we just kind of follow it down here, and then we cross over and we follow it up there. But I stay inside the red for every time after some big n value. So this guy, he just kind of wiggles around, stays in. Okay, so as long as this is true, no matter what epsilon I pick, and if I shrink that red envelope down, I just have to go farther out in the sequence, and I still get these wiggly functions inside that envelope. The farther I go out in the sequence, the closer they are, the smaller that envelope around the function is, and the tighter those functions in the sequence have to be to f. Okay, so let's look at these other pictures here. So these do not converge uniformly to 0. So let's draw an epsilon envelope around 0. So let's pick just epsilon to be 1/2. So if this was to converge to 0 uniformly, there would be some point in the sequence that all of the functions, all of my red, yellow, orange, green functions would be inside this blue region here. And obviously, none of these functions stay inside the blue region, so they can't converge uniformly. Same up here. If I take an epsilon of 1/2 around 0, then all of the functions would have to stay inside this blue region here, but none of them actually stay inside the blue region. All of them are sort of in some sense far away from 0. So these converge pointwise, but not uniformly. Okay. If I have uniform convergence to a function f, though, I do have pointwise convergence, right? So uniform convergence is quite a bit stronger, right? The same as uniform continuity is quite a bit stronger than just continuous at a single point, or continuous. It's that the same n works no matter which epsilon I'm given and no matter which x I pick, right? So if I pick a single x, I can use this n that I got from uniform convergence to show convergence at that x value. Okay. So uniform convergence is stronger than pointwise convergence, but it's harder to achieve. Okay, so let's see how we're going to use uniform convergence. And if you recall, when we were talking about series of functions, we had this Cauchy criterion where if you eventually got far enough out in the series, the sum, the tail of the sum between any two partial sums was small enough that we could say, if that's less than epsilon, I definitely have convergence. I didn't actually have to figure out what things were going to converge to say that I had convergence, right? If I was going to try and use this definition directly, I'd have to say what f is so that I could use this epsilon definition. Well, we're going to come up with a Cauchy criterion for functions and say, well, if this Cauchy criterion holds, the sequence of functions actually converges, and it's going to be very similar to the Cauchy criterion that we had for sequences in series. So let's write this down. Here I'm going to call this Cauchy criterion for sequences of functions. And the theorem says the sequence f mapping e to r, f sub n mapping e to r, converges uniformly on E if and only if given epsilon bigger than 0, there exists n in the natural numbers such that for any m and n bigger than n, we get f sub n of x minus f sub m of x is less than epsilon for all x in E. Okay, so this is really similar to our Cauchy criterion for sequences and series. I've just put in the functions instead of just the s sub n's or s sub m's. I've got functions, and it has to hold for all of the values of the function, no matter which x you pick. Okay, so let's prove this, and we're going to rely heavily on the Cauchy criterion for sequences, because now I've got this sequence f sub n at x. I'm going to choose a specific x and show that I've got the Cauchy criterion there, so it's going to converge. So let's do the forward direction first. Suppose f sub n converges to f uniformly on E. Then let epsilon be bigger than 0. There is an n and n such that the absolute value of f sub n at x minus f at x is less than epsilon over 2 for every x in E. It's not supposed to be blackboard bold. So for n and m bigger than this n, we get the absolute value of f sub n at x minus sub m at x is less than, well, let's just go straight equal to first f sub n at x minus f at x plus f at x minus f sub m at x, which is less than or equal to, by the triangle inequality on just real numbers, f sub n at x minus f at x plus f at x minus f sub m at x, which is less than epsilon over 2 plus epsilon over 2 equal to epsilon. Okay, so if I have uniform convergence, the Cauchy criterion holds. The other direction is slightly more difficult. Not much though. So let's go this way. So suppose the Cauchy criterion holds. Then for x in E, we have the sequence f sub n at x, which is a sequence of real numbers. So this is a special x, a fixed x, so maybe I'll call it x sub naught, or x naught, x0. And this sequence is Cauchy. Cauchy criterion holds for this sequence, we call it Cauchy. So it converges to some value. Say y. We'll define f mapping e to x to r by the limits of these sequences. F of x naught equals the limit of f sub n of x naught. So that's how we're going to define our function f. And this is a good definition because we know that this sequence converges. So this would be y. And we'll do that for each x and e. So I get a defined function that we sort of think that our limit of f sub n should be approaching. Right? So I want to show uniform convergence. I first find something that it converges to pointwise. Pointwise was easier to do. We've shown pointwise convergence to f. Now we have to show uniform convergence to f. Okay. Okay, so let epsilon be given. Then choose n such that f sub n at x minus f sub m at x in absolute value is less than epsilon for all n and m bigger than capital N. Now this is a sequence of real numbers. I can fix n and then I can take m and I can create a sequence, say s sub n is equal to the absolute value, say s sub m is equal to the absolute value of f sub n of x minus f sub m of x, and this sequence depends on m. We'll fix n, and then the limit of f sub m is less than or equal to epsilon, right? And this limit is also equal to f sub n of x minus f at x. So this f sub n at x minus f at x in absolute value is less than epsilon or equal to epsilon. Since epsilon was arbitrary, we can use n and epsilon as the pair for uniform convergence. Okay. So we know that this thing is true for all n bigger than n, and we get uniform convergence there. Okay. If you're worried about the equality there, we can just take epsilon over 2 in this situation right here. You can go over 2. Let me do that in red. Over 2, and then you get a over 2 there, which is strictly less than epsilon if you like. Okay. So that shows that the Cauchy criterion and uniform convergence work nicely together for functions. We're going to use these in the next couple videos to show that uniform convergence of continuous functions are continuous, and the uniform convergence of a differentiable function is still differentiable. The uniform convergence of an integrable function is still integrable, and the derivatives of the functions converge to the function's derivative, and that sort of thing. So we'll see that in the next couple videos.